Good morning, sir. I am Salma Farhat from Triple EB section. Today I am going to tell about scalability and stability in quantum technologies and why it is important nowadays. So here is my topic: scalability and stability in quantum computing. So why scalability matters? From qubits. Sorry for the inconvenience. uh, why scalability matters from qubits to quantum advantage. The qubit challenge, here are three steps. The qubit challenge, first one is the qubit challenge, second one is the unlocking quantum advantage, third one is the need for integration, so its needs and its applications. So the qubit challenge, current quantum system often have a limited number of functional qubits, so typically below 100. While coming to unlocking quantum advantages, true quantum advantages is solving the problem intractable for classical computing requires thousands of stable qubits. For classical computing, it's take only one binary number like 0 or 1, while quantum computer takes two at a time simultaneously, like 0 1 at a time. So the need for integration is scalability demands for just more qubits, but seamless, low error interconnection and control over large arrays. So the challenges of qubit coherence and error rates. The qubit stability is defined by its coherence time. Coherence time means the duration during the qubit can maintain a stable quantum state for while time before coming to the environmental noise. While decoherence, it's opposite of coherence, so it cannot maintain it cannot maintain time or stable, it cannot stable during the qubit, it cannot maintain its quantum state, it loses its quantum state. So while coming to its factors, external factors like thermal fluctuations, electromagnetic interference and vibration disrupt the duplicate quantum states, leading to errors. So high rate errors, where we get high rate errors in quantum computing means present day quantum computing gates have error rates. Quantum computing gates like Pauli's gate, X gate. So these are some examples. These rates that are too high, reliable computation requires error rates to be significantly lower that than current state of the art. So architectures for scalable quantum systems. While coming to scalable, there are three different types of physical implements in scalable quantum system, like trapped ions, superconducting qubits, silicon quantum dots. While coming to trapped ions, ions healed by electromagnetic fields offer excellent coherence time and high gate fidelity. Scaling involves moving ions or using photonic links. Superconducting qubits based on microchips. These are easily fabricated and integrated using semiconductor processors, making mass production viable for scaling. And silicon quantum dots leverages existing silicon fabrication infrastructure, potential for dense integration and long term industrial scaling. So here is the small um, expansion of modular design of for expansion beyond qubits. Like in middle there is a quantum module, central hub, a coordinating model processor, While coming to first one, quantum interconnect, high fidelity communication links, and second one is satellite module B, remote processor for additional capacity. And while coming to third, satellite module A, satellite module A and satellite module B. So achieving stability. So error correction codes and fault tolerance. Here is the some picture regarding to physical qubits are inherently unstable. The path to practical quantum computing relies on sophisticated error management. So the picture shows that the qubit is unstable because it has to rotate around its nucleus, so it jumps from higher level to lower level or lower level to higher level to maintain its stability. So in classical, while coming to quantum, it has somewhat logical qubits or and fault tolerance. While coming to logical qubits, a logical qubit is encoded using many physical qubits to protect the stored quantum information from errors. So it uses a number of physical qubits to protect the information from errors. And fault tolerance requires the capability to perform computational operation on logical qubits without the introduced errors cascading throughout the system. Mitigating noise, advanced control and cryogenic environments. So it has somewhat techniques to reduce decoherence, cryogenic environment and precision control techniques. So while coming to cryogenic environments, superconducting materials and silicon qubits require a near absolute zero temperature to minimize thermal noise and preserve quantum states. And coming to precision control, employing dynamic decoupling sequences and pulse shaping to actively suppress a specific noise source and extended coherence time. Benchmarking process, metrics for success, fidelity, Q volume and coherence. While coming to fidelity, gate fidelity, the probability that quantum operation performs its intended function correctly, I'm eyeing for 99.9%. While coming to quantum volume, a holistic measure assessing the combination of qubit connectivity and gate error rates in the working system. So coherence time, the duration for which qubit can reliably hold information crucial for executing long complex algorithms. So it is about coherence time. So while coming to real world applications where the scalability and stability are very crucial. So drugs, first application, it is used in drugs discovery and material sciences. So it is used in like medicine and all instruments used in medical and material sciences. So simulating complex molecules and chemical reactions requires stable statements with hundreds of thousands of logical qubits. So as I said before this, optimization problems, tackling logistics, financial modeling and machine learning requires large scale fault tolerant quantum processing power. Overcoming hurdles for practical quantum computing. So it should have modular design, fault tolerance, engineering precision. So um, uh, sorry first coming to modular integration, developing high performance quantum interconnect to link modular processing units reliably. So fault tolerance, achieving and exceeding the error correction threshold to create robust logical qubits that can sustain computation. So engineering precision, moving from laboratory scale prototypes to industrial grade manufacturable quantum processors. So with this, I will end my presentation. Thank you.